We have one more talk after this, and then we will start a panel discussion. So let me invite next speaker, Dr. Yaron. He's chief scientist in Ajinomoto Genetics Co. Limited in South Korea. Dr. Yaron Silberberg has completed his PhD in bio-nanotechnology at University College London, researching cell biomechanics using atomic force microscopy. He continued his research at Kyoto University and at the Advanced Institute for Science and Technology as well as at the MIT. He has developed microfluidic devices for in vitro diagnostic of IVDC. He joined the University of Tokyo in Japan as associate professor, and he is currently leading the media feed development in Ajinomoto. So his title of the talk is Advanced Technologies for Media and Process Optimization for Biological Manufacturing. So let's welcome Dr. Yaron.
Thank you very much.
Thank you.
Should I use this? Thank you, Dr. Gupta, for the nice introduction. And thank you also for Dr. Watnesh and all the organizing of the conference. Thank you for inviting me. It's really nice here. And I hope I'm not going to get another blackout here. At some point it will come, I'm sure. So my name is Yaron Silberberg, and I'm Chief Scientist and Head of the CELIS Solution Center, which is the Customer Solution Center in South Korea. Ajinomoto Genexine, just quickly, is a joint venture between Ajinomoto, a Japanese company, and Genexine is a Korean biopharma company. We exist now for 10 years, and we manufacture and develop cell culture media. We are not as huge as Thermo Fisher yet, but we are getting there, I hope. My talk will be a bit similar in some way to Stacy's talk because I will talk about media development a bit, but I will focus on some other aspect that I will show you. First of all, what is CELIS? CELIS is our brand name, kind of short for cell specialist or cell first. And it's based on more than 100 years expertise of Ajinomoto in amino acid manufacturing. Ajinomoto is as you might know, is the biggest manufacturer of amino acids in the world, and we also manufacture supplements, amino acid supplements, also for biopharma and for nutrition industry. But in the past 20, 30 years, we've been developing also cell culture media, specifically for CHO cells, and also for stem cells, MSC cells and iPS cells. So I will focus on CHO cell media in this talk. We have a couple of customer solution centers, and they are basically in Asia. Our main customer solution center is in Korea, which I'm based. And in Japan, we have the main R&D center. In China, we recently opened a new customer solution center. And in India, we are opening also now a new customer solution center in Ahmedabad. Now, our center in Korea is based in Incheon, in an area called Songdo. And it's nearby Seoul. It's about 20 kilometers from Seoul. It's only about 25, 30 minutes from Incheon Airport. So you're all welcome to come and visit our new center. It's located in a very nice building and quite a big lab with a full upstream equipment, amber, and also bioreactor scale, and also media dispensing robotic systems that allow the kind of quick media development. So I will be a bit quick because I have a lot to talk about. So I will try to kind of quickly go at the introduction and then spend some more time on the details of the main development topic. So just a quick overview of my talk. I will quickly talk about the DOE approaches that are traditionally used, a bit like the previous speaker was mentioning about multivariate analysis, DOE experiment. And then I will mainly mention about the multi-omics analysis that we are now developing, how we perform metabolic flux analysis. I will show you two case studies, one for basal development and more recent one for feed development. I will also mention about some more process-related in silico analysis, which is being done together with In Silico Biotechnology, a company. It's a digital twin used for basically optimizing feed-in manner. And I will lastly talk about some other supplements we provide to customers for increasing titer. Oops, sorry. So that's a very general overview. As you already know, cell culture media is used for the beginning of the cell culture process for biomanufacturing. And for the first month or so, sometimes longer, cell culture media is used for cell proliferation and production of the product, antibody or any other protein. So this is only some small part of the whole biomanufacturing, but this is the most important part where all the yield is produced, the drug is being produced. Also, critical quality attributes are quite determined by the process and the media at that scale. So that's why it's quite important. And I also want to mention about the complexity of cell culture media. It has between 50 to 100 different components. That's why it's so complicated and difficult to optimize it. Like was mentioned before, vitamins, amino acids, trace metal, lots of other components that can affect the titer or the yield of the protein. So the basic overflow for evaluation or for development of media is generally like that. For first, we have to adapt the cell line to some new medium we are testing. We perform batch and fed batch tests sometime together using shake flask, spin tubes, or amber systems. At this stage, which takes a few weeks, the main culture is performed, and at that stage, we can see the next two stages, the basic optimization and advanced optimization. That's the stages of development. And you have some basic development, which are, try to show with the laser, but maybe it doesn't work. So the basic development is more about optimizing the feed-in manner, different process parameters like temperature, pH, dissolved oxygen, and also supplementation. For more advanced optimization, it's really dealing with the component of the media, amino acids, vitamins, other components, and also protein quality characteristics like glycan profile and charge variants is important to address at that stage. These stages can take between 1 month to more than 4, 5, 6 months. It really depends on the requirements and the goals of the company, then how much titer they want and how much range of change in the charge variants or glycosylation, for example. So just quickly about kind of a first immediate thing that needs to be optimized when we want to get the best of a cell line. Feeding is usually done originally according to the manufacturer recommendation and 2 or 4 or 6%, but it really depends on the cell line and the protein, and it's really important to do this kind of design of experiment to investigate a few feed-in manners. So that's kind of basic feed-in manner optimization that uses 2 and 4 and 6%, sometimes even more than 6, depends on the cell line. And starting of the feeding in a fed batch can start at day 3 or 4, and it's really can make a difference. In this example, it doesn't make so much difference between day 3 and 4, but 2, 4, 6%, you can see the titer can increase and double between two feeding manners. In some cases, some cell lines show better performance in 2% in low feeding. So it's really important to test not only high, but low feeding too. Related to DOE, when we want to optimize media and basically deal with the component and see which components are more like a bottleneck or a critical factor that we need to adjust, you can perform a basic DOE, which is done like this. You can choose a few amino acids, for example, in this case, 4 different amino acids, and perform a full factorial design. This shown, for example, 16 different combinations of the 4 amino acids. And then in our lab, for example, we use a robotic powder dispenser that can create any kind of formulation. And then it's been automatically done and quite quickly. Then we perform it on amber, the cell culture. We perform the main culture on amber system, and then doing some amino acid analysis. All this data can be incorporated into multivariate analysis to check PLS, for example, partial least square system, to see correlations between components. And this data can give you, for example, a few cases when you get a higher titer, like for example here, or higher VCD. In blue you can see the titer, so it's increased a bit. And it can give you information also about number 2 that says the synergetic effect. So different amino acids can interact with each other and some kind of combination effect. So that is useful for that. But all this kind of theory doesn't give you much information about the mechanistic level, the science behind what's happening. So you don't know the reason, the metabolic pathways which are affected, and how it affects cell behavior and productivity. So for that, there is a kind of a more deep and new emerging field which is called the multi-omics. Metabolomics or proteomics, genomics are all gathered together what's called the multi-omics. Computer biosimulation takes into consideration the whole cell model, all the metabolic pathways, and the advantage of this is better representation of the cell, and we are able to identify really the rate-limiting steps, so the bottlenecks, the metabolic pathways which can really affect the productivity. And that's really case by case. And the performance and productivity can be improved, and also protein quality can be addressed. So that's a kind of more new field about how we can actually use this system to control the glycan profile and charge variants. But I will mainly talk about the performance, the titer in this talk. Just a general flow of how the workflow goes. So we basically currently doing amino acids specifically, analysis of consumption rates, and then we incorporate it in a global metabolic network, looking at all the metabolic pathways and looking at which areas are more increased in flux, which reaction were more increased in the flux rate. And then we're actually looking at individual reaction. So this model is incorporated more than 7,000 specific enzymatic and metabolic reactions. And it was built based on literature and research from hundreds and hundreds of papers. 3 different groups in the world was actually building this kind of model and incorporating together to build it. And we are collaborating with one of those teams, and I will mention that. So recently, or last year, we published this paper, which deals with the kind of proof of concept of how the system can be applied for developing of media. The group is headed by Professor Dong-Yap Lee from SKKU University in Korea. And what we do here in this study, I will really go quickly. I won't get into details, because in the next case study, I will go into a bit more details. But in this case study, we're looking at basal media development, or investigation into basal media effect. So we use, as you see on the left, 2 K1 lines, K1-1 and 2, and 2 different media, basal A and basal B. The whole workflow starts with first performance data and analyzing basically the consumption rate of amino acids and basic elemental balancing, so carbon-nitrogen balancing, in order to process the data to fit it well. And then comes the statistical part. So the statistical part includes multivariate analysis, and it finds correlation between components. So we can find which components are correlated to each other and which ones are correlated to affect more the performance, the productivity. Finally, and most important, is the metabolic analysis, which is part of the model-guided analysis. So that's basically the genome scale model that, as I mentioned, built on existing data that gathered on hundreds of different cell lines or cell clones, all are CHO clones, and kind of incorporate all the metabolic all the metabolic pathways and more than 7,000 reactions. So it's give kind of a general model of the cell. Just one of the advantage of this use of this system is that we are not investigating effect on a specific clone, specific cell line, or a few cell lines, like a normal DOE for developing of media. We incorporated this media to find general factors, really factors that affect in general any kind of cell line, but we are checking it with specific media on a specific cell line. So it really highlights the important bottlenecks. And just quickly mentioning here, the statistical element here found some important metabolites that are high with the VIP, the variance of projection, variance of importance in projection, which means those elements, those components are more correlated to significantly affect the productivity, the titer or the growth. So after doing this statistical analysis, we look at the components and the pathways which have more impact. And then we are looking at more metabolic flux analysis. And here you can see the different rates of, for example, glycolysis and TCA cycle. And we can look at which nutrients are being more depleted. And this is all simulated, right, according to the data of only amino acids that we input. Again, I'm doing this very quickly. I will go into more details in the next case study. But in this case study, we found that there was a limited pool of FAD. Sorry. Oh, no. Okay. FAD plus. So in some cell line and media combination that you see on the left bar, we got a quite limited pool of FAD plus. And the thing is that this is related to the electron transport chain on that metabolic pathway, which is highlighted there. And the model identified a key component, which is coenzyme Q10, that has a chance of affecting the cell growth in this case. And then validation experiment followed to look at the different cell line and media combination. And as the model suggested, specifically for that cell line number 1 with media A, increasing adding coenzyme Q10 really increased the VCD here by more than 30%. And it didn't happen in other cases because it was specifically for that cell line. Now, this was about basal. Related to feed, this is more recent research we did. And this is also in collaboration with the SKKU University in Korea. And in this framework, we looked at the feed specifically. So we use one basal. Sorry, in this case, we use 2 basals, and we use 2 feeds. So the combination was done on one cell line. A general workflow is basically to get the culture profile to compare the performance data between different feeds and get some statistical data, multivariate analysis, and at the same time later get model-guided analysis and basically do the metabolic flux rate analysis. And then finally, have some hypothesis about which ingredients are important, and then formulate a new feed. It's for 4 conditions, A1, A2, B1, B2. So A1, A2 is basal A with 2 different feeds. B1, B2 is basal D with 2 different feeds, the same feeds. We will mainly focus on A1 and A2 in this example. And if you look here,
you can use the mic now.
Yeah, so if you look at this VCD chart, you can see that the blue line represents feed 1. The red lines are feed 2. With the feed 1, we got quite high high VCD here, high peak VCD. But at the same time, with the feed 2, even though the VCD was low, the titer was much higher. So some element in that feed might increase productivity rather than cell growth compared to A1, feed 1, which more encourages cell growth, but then the drop is quite fast. So feed 2 encourages longevity of the culture slightly and more titer. So the strategy here is basically to identify which components and which pathways are most different between those 2 feeds. Because those components which are most different between those 2 feeds, or these pathways or enzymatic reactions.
Sorry, Yaron. Sorry to interrupt in between. We are running short of time. We have 2 minutes to wrap up.
2 minutes, okay. And basically, the idea is to find the components that are most different between those. And then we can combine the advantage of those two feeds together. Multivariate analysis is being done the same as I mentioned before. 2 points here, we consider the correlation of feed-in. So the multivariate analysis shows that before feed-in, the components are correlated, and after feed-in, the components, the amino acid consumption rates are correlated. So feed has this very strong effect. And secondly, we kind of target the amino acids which has the highest VIP score, and those components are the ones that we want to investigate for metabolic flux. For metabolic flux, we're using the global metabolism pathway chart. And we incorporate all the metabolic pathways, hundreds of them, and looking at the most important one, that difference between the two feeds. And then we discovered many things, but I'm just highlighting just a few of them. One of them, we saw a very high difference between the flux rate for the single carbon chain for serine 3-PG in the glycolysis, and also glutamate to alpha KG. This is a pathway which was really intensified in the feed 2 compared to feed 1. So those are very different between those two feeds. So we wanted to basically incorporate these elements into the first feed to see the effect on the titer. All the red lines there basically shows that the feed 2 has much higher flux rate compared to feed 1 in that pathway. So then we did a validation experiment, and as you can see, the increase of glutamate in the feed 1 actually increased 20% in titer, according to that results that the model-guided analysis provide. And this is just for one amino acid that we can reveal. Of course, there are a lot of other components that we actually adjusted in the new feed and got results which are much better than the previous feed. And just to show you just some kind of data we got recently for K1 line and for CHO-GS line. So the titer we received was quite high, more than 10 grams per liter. And in the lower graph for the CHO-GS line, we investigated quite a popular basal feed combination in gray. And our combination of basal and new feed gave us double than the reference. So it was quite successful new development for the new feed, and this feed will be released soon. So quickly, I know I don't have too much time, but still, I want to mention quickly a collaboration that we are having within Silico Biotechnology. It's a company based in Germany and Singapore. If you have questions about this, please come to our booth, Celis booth, later, and I can discuss more about this. But basically, it's an alliance we started with them for developing of feed and feed-in manner using a digital twin. And the idea is to do it very quickly with only one wet experiment, a quick development of digital twin that's done in less than 2 months. And this kind of development, we either get the cell line from the customer or just the data. We can do the analysis of amino acid consumption rate, share the data within Silico Biotechnology. They produce a digital twin model, and then we can give, in a couple of weeks, an enhanced feed-in manner and also enhanced formulation of feed. Just an example, just touching the feed-in manner alone, without touching the feed, led to 60% increase in titer. So we are employing dynamic feed, which means 20 different feed-in manners we received from the digital twin, and we found that two of these feed-in manners gave 60% higher titer than just the control feed. And finally, just mention the amino supplement, which is a new supplement we developed also to be able to add to the feed to increase titer and increase the feed stability. It's a cocktail of different components, including cysteine, which increase stability and titer. And almost last, this is our center in South Korea, and CSC stands for Celis Solution Center. If you need any help, remote help, or cell adaptation screening, media development, even scale up, we are ready to do it, and we support global customers. And finally, just to say thank you for all the members that their research incorporated in these presentations, including the groups in Kawasaki, in Japan, and in SKKU University and in Silico Biotechnology. Thank you very much for listening.
Thank you very much, Yaron, for very informative talk. Omics and AI approach is the future for the process development.